Yeah, though we have seen really very significant advances to make structure-based drug discovery on membrane proteins feasible, as it was feasible for soluble proteins, kinases, proteases, and so on, such drug targets, let's say 20 years ago. I'm talking about on behalf of a company, leadXpro, which is located in Switzerland, next to Basel. So what we are doing in a nutshell, we have established a platform of first here starting. I don't know if you can see my pointer. I maybe start the laser pointer here. Do you see it? So it starts with expression of the protein. So you know membrane proteins, we work mainly with human membrane proteins. They need to be expressed in human cells, in mammalian cells, or in insect cells. First, you need to prepare the membranes and then extract the protein and purify the protein. And here it is very important also to do a very good quality check, that you look, for example, at cryo images here. And you see here, for example, a very great homogeneity of the sample. And then, of course, the classic biochemical tools like size exclusion chromatography, as well as SDS gel. So really very pure protein, very nice protein, well-behaving protein, functional protein to do three things mainly. First, biophysical methods. And here we have a number of technologies in place. I come to this in a minute. And then second, X-ray crystallography. So we crystallize the protein and then do X-ray diffraction experiments, like here seen on the left-hand side. And this is typical for GPCRs here, for example, CCR2, chemokine receptor 2. Here we see the ligand very well fitting into the electron density. And here this is in collaboration with Boehringer Ingelheim. On the right-hand side, we see an ion channel structure, which was determined using a technology called cryo-electron microscopy, cryo-EM. And you see also cryo-EM today is able to enable visualization of small molecule ligands. You see here on the left-hand side in green this ligand, well-defined with X-ray crystallography, but also with cryo-EM today we are able to do the same resolution and solve the structure. In order to be successful, we need to do a couple of things very well. So it starts with protein generation, and here important is to engineer the protein. So to introduce, for example, here a number of mutations, also to engineer loop regions, for example, in order to make the protein more stable, as well as well behaving with respect to purification, for example. Here, crystallization is more demanding, so we need to engineer more compared to cryo-electron microscopy, because here we work more or less in solution and then shock freeze, cryo freeze the sample, and consequently no crystallization for the sake of discussion is required. In order to screen for many constructs, mutations, and so on, you need to be able to do this. And here we have established a pipeline really to screen, for example, here 130 constructs in just 4 weeks. This is exceptional and not easy to do and requires a significant infrastructure. What we are aiming for is always to improve the thermostability of the proteins. And you see it here, the introduction of these mutants improved by more or less 10%, the 5 to 10% of the thermostability. Sometimes in projects, after the combination of mutants and so on, we achieve more than 20 degree of thermostabilization. And this shifts then the stability from maybe 20 degree, 25 degree to 45, 50 degree. And this is very important because even if you work on at 4 degree, the protein requires some stability to have purification and then cryogenic freezing or crystallization. Very important for us is the control of the ligand binding, and this is done by biophysical methods. Here we have mainly two methods we work on. Here on the on the right-hand side, we have the so-called thermo-shift-based assays. That is a nano-DSF here, or with dye labeled technologies, like we can do this investigation of the thermostability. Here important to see is after addition of the ligand that we see another improvement in the thermal shift, indicating that the ligand really binds. This is very important. We can do it with a second method, and this is it's a so-called Cryo-Optics wave delta method. It's an SPR-like method where you immobilize your protein and then measure the on-off rates and the binding kinetics of your small molecule ligand, for example. And this is, of course, very important to also prioritize ligands for later structure research. Here we also apply often a trick, let's say, because we generate so-called binding proteins that are easy to measure. And here nanobodies are very important in our research. Nanobodies, these are special antibodies. So humans, mammalians, they have usually antibodies. But in addition, some animals like alpaca, sharks, for example, as well, they have special antibodies called nanobodies. And they are just VHH antibodies, if you want, so they have just one single chain. And consequently, they have this is a very nice tool, and this can be used in structure research. For example, for binding methods, also to validate our methods for small molecules. Or we can also use the nanobodies to form complexes to improve structure research. And here's one nice example of a bacterial transporter. We have worked with two of these binding proteins to improve the resolution. Another example is here. We have established nanobodies against GPCR. In this case, the nanobody shows even specificity to bind to an GPCR here with an agonist conformation or with an antagonist conformation. So this is the beauty of these nanobodies. They are super, super specific to a certain conformation of the protein. And this can be used here, and this was a collaboration with Mike Sharp and Dome. And you see here the binding curves really are indicative that some of the nanobodies only bind to the agonist conformation. Of course, this could be very well used here in a complex formation of the G protein. Then the receptor, in this case, it's orexin 2. And then here the nanobody, or in this case, it's a synthetic nanobody, it's called Cybody, is bound here on top and improves the binding affinity. That can also, very same technology can be applied to antagonist GPCRs, like this one here. And also here, this enables cryo-EM structure determination. Finally, I would like to share with you a bit more details on the project I showed already earlier. This is an ion channel. It's a potassium ion channel, KV 3.1. We have just published a few days ago with the company Lundbeck here in Denmark. First, we have investigated different detergents here. We measured with biophysical methods the ligand binding, and you see here is very nice visibility of the ligand. And here a close-up view, really you see each and every side chain of the protein is determined, as well as the ligand density. Okay, and for the question, of course, you might ask is, what is it good for? And it is good for the enablement of structure-based drug discovery. And here we have multiple options to work. One, and very dominant, is in silico screening. So you are all maybe familiar with high throughput screening. The screening in a biochemical assay, for example, or a cellular assay of a huge compound library. These compound libraries can be from a couple of 10,000, 100,000, and large corporate libraries are even millions of compounds. And of course, if you do then these screening methods, apply it, then this is a significant investment. It's easily 1 million and more you invest for a high throughput screening. But you can also do a screening in silico, in a computer, using computer programs depicted here. So this is done here with the Schrödinger software package, computational chemistry software package. And here the program takes from a virtual library that is stored in a computer. You can screen through all these compounds and then create a much smaller set of structures. So first you can start with a huge library, here in this case 6 million. That is significantly more than even the largest corporate libraries have in compounds. Then you screen in silico. You end up here like with a selection of 120 compounds. And these 120 compounds you can purchase from vendors, chemistry companies who are specific about being able to create these compounds. And then you purchase these compounds, and then you just test 120 compounds in an experimental setup. And this is, of course, a huge cost saving compared to an HTS campaign. Okay, I hope I could show you a bit of a glimpse of how membrane protein structure determination has improved recently. So I showed to you that the quality of the protein is key to be successful. So we do rational design of constructs, introduce mutants and so on. We screen for optimal conditions for detergents and buffer, and provide then the protein for antibody, nanobody generation. We can also use like a DNA encoded library screening. And then we apply it for biophysical methods, for binding kinetics, as well as to prioritize really for structure research. And then we can solve structures by cryo-EM or X-ray crystallography. And here also nanobodies and such binding proteins in general are very helpful. On the right-hand side, this picture here shows a movie that's a computational simulation between two conformations that were solved by cryo-EM. First, the APU structure in a closed conformation of the ion channel, and then the agonist bound molecule in the open conformation. So the agonist binding indeed opens up the ion channel and enables that there's a full conductivity here for ligands for these for this TRP channel. And this has been a collaboration with Bayer Berlin. Okay, with this I end up with